All right, welcome back again. Today we're going to be talking about actually the last two convergence tests that we're going to use in this chapter, the ratio and the root tests. So let me get the slides pulled up and we'll get started. All right, there we go. Right. Okay. Oh, so the good news is this section is actually quite short. It's really not that long of a section, but these two tests are critically important. They get used a lot. In particular, the ratio test gets used a lot, and we're going to use it a bunch in the remaining sections of this chapter, like in particular, like 11.8, 9, 10, and 11. So the overview is very brief. The overview is just the ratio test. And then the root test, we're going to get the statement of the theorem, talk a bit about their use, and then do some examples. All right, so here's the ratio test. Given some series, we have three possibilities here. This says if the limit of a sub n plus 1 over a sub n in absolute value is equal to some number that's less than 1, then your series is absolutely convergent. Boom. That's nice. However, if the limit of the ratio a sub n plus 1 over a sub n in absolute value is greater than 1, then your series is divergent. Boom. The end. Now, if this ratio or the limit of this ratio is equal to 1, then the test is inconclusive. So in that case, you've got no result and you have to pick a different test. But this is really, really quite nice, right? This is saying all you need to do is test a limit of a ratio. And if that limit happens to be a number that's less than 1, then you automatically know that your series is absolutely convergent. And here, if you test this limit and you get something that's bigger than 1, you automatically know that the series is divergent. So this test can be very quick to use once you get comfortable with it. So some notes about it. Oh, yeah, so we omit the proof. Once again, I apologize, but you can read it in the book. It's on pages 812 to 813. If you want some intuition for what this theorem is saying, it's saying that if the ratio of consecutive terms is less than 1 in the limit, then the convergence can be compared to that of a geometric series. That's really what happens. And if I remember correctly, I think that's what you do in the proof. Oof, but I can't remember off the top of my head. I can't remember off the top of my head, but I'm pretty sure that's actually how you prove this result. Uh, yeah, basically look at the ratio of consecutive terms, and then you can start to look at how it compares to a geometric series, which we know converges when r is less than 1. An important note here, and I'll say this in the next section as well, in practice, the ratio test is really useful when your summand has a bunch of products in it, a bunch of products in it. So for example, n factorial. If you've got n factorial or you've got like just a bunch of stuff being multiplied, then the ratio test can be really, really useful. It is not so useful when your summand has a bunch of sums in it. So for example, ln of n plus 1. So the ratio test is not a very helpful test when you have expressions like this that pop up, mainly because you are hoping for some kind of cancellation. You're hoping for some sort of multiplicative cancellation through this process. And when you end up with stuff like this, or even like um, uh, trig functions of sums or differences, it can get really, really messy really, really fast. And so it may not be the best test to use when you have stuff like that involved. So um, it's not the best test ever. It's not a test that you want to just throw at everything. But if your summand has a lot of products in it, maybe try the ratio test. Um, oh, yeah, another thing right here. So the ratio test usually works when the summand contains an exponential, like e to the x, or if it's got a factorial, but it will always fail for p-series. So if you've got something that's looking like a p-series, the ratio test actually will not help. Just a little heads up about that. Okay. Let's practice. Let's determine if this series is absolutely convergent, conditionally convergent, or divergent. All right. Now, the first thing I notice here is that the summand has a lot of products in it. It's basically -3 to a power, and it's some factorial in the bottom. there's a lot of stuff being multiplied inside there. So maybe the ratio test will be easy to use. So here we go. Oh, just what I said. So we're going to use the definition of the factorial function, and we're going to do a lot of diligent algebra, which I'll walk through carefully this first time. And here we go. So initial note, remember this is the limit that we are exploring. So this is where you kind of want to just take a deep breath, write down what the limit is equal to. Don't let it overwhelm you. Don't let the messiness get to you. Just write it down step by step, little by little, and then we'll go through the pieces. Okay? So this is the limit we need to evaluate. A sub n plus 1 is just the summand with n plus 1 plugged in for n. And that's what I've got right up here in the numerator. I'm going to zoom in a little bit. There we go. Oop, come back, come back. There you go. Right. There we go. Okay. So this piece right here is a sub n plus 1. And then down here is a sub n, right? Let's see, what did I do first here? Oh, first I just simplified what was in the factorial. So 2 times n plus 1 plus 1, I changed to 2n plus 3. And the next step is to basically flip and multiply. So rather than deal with this very funky looking compound fraction, we're going to take the denominator, we're going to flip it, and then multiply to get this next expression here. All right. Since we're at this point, it is common, and I will do this very often, and I'm pretty sure many of you will also do this very soon. It's common to just skip this entire step and just go right to this step. Common to skip it and just write it as the product of the reciprocal, just to save yourself a calculation step. All right, now let's keep our eye on the ball here for a minute. We're still just trying to evaluate a limit. So even though this looks super duper messy and it's got to be cleaned up quite a bit, we're just trying to evaluate a limit. That's it. So any techniques that you have used to try to evaluate a limit are fair game here. We're just evaluating a limit. So here's usually what goes down with these types of ratio test problems. We're going to cancel as much as we possibly can. This is why products are nice. So for example, we've got n plus 1 negative 3's up here, and we've got n negative 3's down here, which means we can cancel n of those factors. We can cancel n negative 3's, and what we're left with is just 1 negative 3 right here. That's it. That's all I did with the first step. Now we're going to deal with the factorials, but remember, the factorial has a recursive relationship. So 2n plus 3 factorial is, oh wait, what did I do? Did I cancel it? Oh, I didn't cancel it yet. I dealt with the absolute value first. I'll get to the factorial in the next step, right down here. What I'm doing now is dealing with the absolute value. So this is a positive factor. This is a positive factor. So absolute value of it is just that factor again. The only place the absolute value will apply in this case is to, or I should say, where it will change the expression is to this negative 3. It's going to make that a positive 3 instead of a negative 3. But remember, constant multiples can be pulled outside of the limit operator, so we get 3 times the limit of this bit. Now we just have to deal with this bit. And this is where the definition of factorial comes in handy. 2n plus 3 factorial is the same as 2n plus 3 times 2n plus 3 minus 1 times 2n plus 3 minus 2 factorial. So all I'm doing is I'm rewriting this factor of 2n plus 3 in this form instead. I'm sorry, 2n plus 3 factorial in this form instead. Okay, take a look at that and just think about it for a minute before I move on. Just try to make sense of how I went from this step to this step, because you're going to do that step a lot in these types of problems. Okay, now let's finish it up. Right at the end here, we've got a 2n plus 1 factorial on the top and a 2n plus 1 factorial on the bottom, so we can cancel those factors. And now we're just left with this limit to evaluate, but this is an easy limit to evaluate. This one is simple to do. As n goes to infinity, the denominators go to infinity, or I should say the denominator goes to infinity, so that means that the whole fraction goes to 0. 0 is less than 1. 0 is a finite number that is less than 1. So, by the ratio test, this series is absolutely convergent. And we're done. Absolutely convergent. That's all it is. That's all it takes. So, one note about this, um, this is a very, very handy test when your series is just right. It kind of just reduces the entire problem to a little bit of messy algebra, but you're all comfortable with this type of messy algebra by now. It's really just calculating a limit. So any of the techniques you learn to calculate a limit apply here. All right, let's do this one. Um, Let me see here. Oh, yes, yeah. I want you all to try this one on your own because it's kind of a cute result, okay? So test the convergence of this series, determine if it's absolutely convergent, conditionally convergent, or divergent, and I'll let you think about it for a minute. All right, now say something out loud to yourself about what you're going to try. Maybe a test that you could use? All right, now try to work it out on your own. Remember to write your calculations as a chain of true equalities, respect the equal sign, be complete, be precise, and we'll do it together in just a moment. Okay, here we go. So, first thing that I notice about this series is it's got a lot of products in the summand. We've got n to the n, we've got n factorial, lots of stuff being multiplied. Let's try the ratio test. Maybe we'll get lucky. So here's the calculation for the ratio test. And I'm now going to skip several steps. This is the ratio that we're looking for, or the absolute value of it, right? Uh, I wrote it like this right off the bat. Remember, a sub n is this thing right here. Maybe I'll even say that's a sub n. So I just multiply by the reciprocal. So rather than writing out this quotient long form, I just wrote it as multiplying by the reciprocal to save myself a step. There we go. Okay, now what I'm doing is just some algebraic massage. In the end, I'm going to try to take a limit. That's really what I'm going to do is I'm going to try to take a limit. So now I'm just kind of massaging things. Um, n plus 1 to the n plus 1 is n plus 1 times n plus 1 to the n, right? And then we've got an n plus 1 down here that we can get out of the n plus 1 factorial. So this becomes this. Now we'll be able to cancel some things, right? We can cancel n plus 1. What else could we cancel? Oh, we can cancel n factorial. And then we're just left with this. Okay, next thing to notice here is we've got this raised to the power n and this raised to the power n. So just by using the laws of exponents, we can pull out that exponent n and write it like so. Okay, remember, got to keep in mind we're just trying to take a limit. We're just trying to take a limit in the end. So all of our manipulation is with the goal of taking a limit at the end. So I'm going to simplify this. I get 1 plus 1 over n to the n. And what does that converge to? That converges to e, the number e, as we saw way back in chapter 6. Way back in chapter 6. Yeah, I think that was the section on L'Hopital's rule where we finally proved that. This limit is e. So the limit as n goes to infinity of this ratio is e. But of course, e is bigger than 1. So by the ratio test, this series diverges. Yeah, it diverges. It's a divergent series. There it is. Add up all these terms, they're just growing too fast. You're going to blow up to infinity. All right, so that is the ratio test. Now let's talk about the root test. So the root test is a similar setup, you could say, but the structure is slightly different. So you start out with a series, just you're given some series. Now what we're going to do is look at the limit of this expression. So we're going to take the nth root of absolute value of a sub n and see what that limit is. So that's the difference between the ratio test and the root test, the structure of the limit that you're investigating. So here we're going to take the nth root of absolute value a sub n. Now, if that limit is less than 1, you've got an absolutely convergent series. If that limit is greater than 1, oh, absolute, there's no such thing as absolute divergence. There's just divergence. is divergent. Yes, there's no absolute divergence, just divergence. And just like before, if the limit happens to be equal to 1, the test is inconclusive. You can't use it. Pick a different test. Sorry. That's really all it is. Okay, some notes and tips about the root test. In practice, the root test is useful when your summand is raised to an exponent. So if you've got a bunch of gobbledygook in your summand, but then you notice that it's also raised to a little power at the end, the root test can be really helpful. The root test can be really helpful. Another note here, if the root test is inconclusive, meaning that the limit is equal to 1, the ratio test will be as well. So there's no use in testing the other one. So if one of these tests gives you a 1, the other test is going to give you the same thing as well. It's not going to give you a different result. Sorry. All right. So, um, let's do this one. Let's do this one. It's always good to I like doing these types of problems because they let us verify that what we originally figured out is actually a good thing to have figured out. That's why I like these types of questions. So, let's test the convergence of this geometric series. And we're going to use the root test to tell us when this series converges and when this series diverges. So here we go. First, we can factor out the a from this series. It's just a constant multiple, so we can factor it out. Then we can look at this series instead. Now, in this series, r to the n is our sequence. That's our summand. So we're going to take the nth root of the absolute value of r to the n. You can pull exponents out of absolute value products, or absolute value factors, I should say. So you get this, nth root of n, they cancel out, and you're left with absolute value of r. Okay, now by the root test, literally this result right here, it says, hey, if the limit is less than 1, it's absolutely convergent. If the limit is greater than 1, it diverges. Check this out. Same result here. If r is if the size of r is less than 1, it converges. If the size of r is greater than 1, it diverges. So this agrees with our previous theorem about the convergence of geometric series. This is another test showing us that these things converge in this way, which is just great. It's great to have more than one verification that something is correct. Okay, all right. Let's do one example. This one I want you to try on your own. You have the idea, you know the basic formula, I should say. So you think about it for a minute. Determine if that series converges or diverges, right? And then say something out loud to yourself, maybe what test you're going to use. All right, and now work it out. So try to compute that limit, see what you get, and determine if the series converges or diverges. All right, let's do it together. So first thing to notice about this series is that the summand is raised to an exponent. Perfect time to use the root test, because the moment we use the root test, this exponent is going to get wiped out, and then we're just looking at the rest of the stuff, right? So that's what we're going to do. Take the nth root of the absolute value of a sub n. Uh, a sub n is this whole thing, but all the terms are positive here. All the terms are positive because this is positive, and n is positive. So the absolute value just gives you the positive result. The nth the nth root and the exponent n will cancel out, and then you're just left with this expression. Divide by the highest power, and you get this, which goes to the number 2/3 as n goes to infinity, and 2/3 is less than 1. Therefore, by the root test, the series is absolutely convergent. All right, okay, that's it. Let's play. So that's that whole section. Like I said in the very beginning, the section's pretty short. The tests are really not that difficult to use. They're very powerful tests, and those are the last two in our arsenal for right now. Those are the last two theorems and tests we're going to get for series until we start talking about Taylor series and Taylor polynomials and so on and so on. All right, so thank you again for listening, and I will see you all next time.